Okay. Okay, welcome everybody to this analysis seminar. So we are recording this seminar, and the recording will be available on YouTube SISSA channel. Now we have Emeric Roulley from SISSA, of course, and he will talk about invariant KAM tori around annular vortex patches for 2D Euler equations. This is Emeric Roulley.
Thanks for the introduction. Thanks for giving me the opportunity to present you today some research on my work, which has been done in collaboration with Zineb and Tawfiq Mehdi, who are both at Abu Dhabi now. So I will talk about Euler equations and some special solutions to these equations, which are quasi-periodic in time, and also who belongs in the vortex patch class. So in an introduction, we will speak about what is a vortex patch, a solution for Euler equation. We'll discuss also some special solutions in the vortex patch class, which are uniformly rotating in time. And then we will move to the more general solution, which are quasi-periodic. So we present the notion and how to obtain them thanks to KAM theory. Okay, so first recall what are the 2D Euler equations. So basically we can write the equation like this, which is a transport equation on the vorticity, which is the curve of the velocity field of the fluid. And the velocity field is assumed to be divergence free, so we consider incompressible Euler equations. So the velocity field is given by the grad part of some functional sign, which is given by the integral of the vorticity against a kernel, which is the green function of R2 in this case. So the fluid is set in all the plane, and the green function in this case is the modulus. So it's a convolution in this case. Okay. So for this type of equations, so transport equations like this, which are nonlinear, we know that if you take an initial condition which is bounded and integrable, then so it's a result by Ludovic, you will have a global in time solution, existence and uniqueness of a global in time solution. Okay, and if you look at the transport structure, then if you take, for instance, vorticity, which is the characteristic function of the domain at time 0, then basically at time t, you will have still the characteristic function of some domain. So it's you can think about it as an evolution. Look at the evolution. If you take the domain d0, and you take vorticity 1 here and 0 here, then at later time you will have another patch. So this is what we call the patch, a vortex patch, which has the same structure, I think. Okay. And also, since the velocity field is divergence free, then the area is preserved. So the area of t will be the same as the area of the initial domain. Okay, and how do you obtain the domain at time t? The domain at time t is given by the image of the first of the initial one by the flow associated to the velocity. Okay, so how to study the dynamics of these type of solutions or vortex patches? Well, basically, you see that all the dynamics is given by the boundary. If you know the boundary, you know everything. So you look at the evolution of the boundary, and so you introduce a parametrization z of t, the boundary, time t. Then, if you take a normal, the normal vector at the position z of theta, so here we are at z of theta. Then, in this case, the velocity of a particle located at this point on the boundary must have the same normal component as the velocity of the boundary itself. So what does it mean? It means that if you have a particle on the boundary, then it will remain on the boundary for all time. So this is typically a phenomenon which appears in free boundary problems. Okay. For those who like water waves, you have the same phenomenon which appears, which gives rise to directly to the main operator. That will represent it. Okay, so this is the equation of interest, and this is called the vortex patch equation. Okay, so let us discuss some trivial solutions that we know that exist for this class of solutions. So if you take a radial domain, then it will be stationary, because basically you have a grad per psi in the equations here. So V is grad per psi. If you take omega, which is radial, this is radial. So the convolution will be radial. So psi also will be radial. And so you have the grad of a radial function against the grad of a radial function. So it will be 0. So this is why it is stationary. Any radial solution. So in particular, if you take a disk or an annulus, it will be a stationary solution. So when you have a stationary solution, you can wonder if close to this, you can find some non-trivial solutions. Okay. And the techniques that you will use to find them, that we will present here, are of two types: bifurcation theory and KAM theory. So let us discuss the first results about periodic solutions, which will be attained by bifurcation theory. So in this case, we look for a domain time t, which is a rotation at some constant angular velocity omega of the first initial domain. So you take your first initial domain, which has center of mass 0, and you make it rotate at some angular velocity omega. Then, if you plug this ansatz in the equation, in the vortex patch equation, you find basically a new equation which is stationary with itself. It's not dependent on time. Okay, and now you have an equation you want to solve. You have a parameter, so you can use bifurcation theory as we chose. Okay, so you can prove, not using bifurcation theory but directly some computations, that ellipses in particular, so they are not radial, they can be uniformly rotating solutions if and only if the angular velocity is related this way with respect to the semi-axis of the ellipse. Okay. So A and B are the semi-axis of the ellipse. So it has been proved by Kirchhoff almost 2 centuries ago. So we wonder about non-trivial solutions, which are not the ellipse, but something else, with maybe more symmetries. So as often, we look at first numerically what happens, and then we try to conjecture something to obtain some solutions. So the numerical simulation has been done by Dim and Zaluski, and they obtain threefold or fourfold domains. So n-fold means your domain is invariant by the action of the diedral group of order n. Okay, so they found this numerically, and then so people tried to prove it analytically, and it has been done by Bourbea in 82. So basically, you know that the disk is a solution which rotates for any angular velocity because it's radial. So you have a line of trivial solutions which corresponds to the disk. Okay, and you wonder if close to this you can find non-trivial solutions, and so you use bifurcation theory, in particular von der Rabinowitz. So I don't know if you're familiar with the bifurcation theory, but basically you have a functional which vanishes, so PD, and you want to, which depends on the parameter omega in this case, and you want to find, you know that you have a line of solutions, and you want to find non-trivial solutions. So you look at the kernel of the linearized operator. It will have kernel of dimension 1. You look at the range, it will have codimension 1. And then under some non-degeneracy condition, you can conclude that for some points for which the linearized operator has a good Fredholm property, you can find non-trivial branch. Okay. Basically, this is the idea. So this is how you got this type of bifurcation points. So for specific angular velocities, actually, your solution can bifurcate in some sense. So can no longer be a disk, but something with a symmetry. So here you have symmetry 2, symmetry 3, symmetry 4, etc. So for any symmetry greater than 2, you have these bifurcation points. Okay. In particular, notice that in this case, the angular velocity of rational with respect to n. Okay. It will be important in the cycling. You can also bifurcate from n equals 1, but basically this is the trivial solution. So you still have the disk, but in translation. So it's not really a branch of non-trivial solutions. Okay. So you can find these branches, and notice that the omega m here is always contained between 0 and 1/2. Okay, so you can wonder what happened outside. And actually, in this series of works, it has been proved that there is nothing about the disk by some variational techniques. Okay. Also, I want to mention that the bifurcation theory of given by Kandar-Rabinowitz theorem is a local theorem. So you construct the branch locally around the trivial solution. Okay. So you can wonder about what happens for the global branch. And there are some theorems. So basically, Buffon-Eaton theorem, which tells you that you can or not prolongate, and if you have some loop or something like this. Okay. So it has been studied by Nash-Moser and Euler that you can actually prolongate the branch. There is no loop. And at the end of the branch, whatever that it means, basically you should have some singularity of the patch. So the patch, if you follow the branch, then the patch must have a corner. So it's a conjecture corner. It's not proved. Okay. So you can also wonder about the regularity of the solutions. So basically, in this paper, he proved Euler regularity. So you do bifurcation in Euler spaces, but actually you can do it also in analytic spaces. And it has been done, for instance, by the Spanish school, yeah. And also in okay. Plus, once you have one branch of solution, you can wonder if there is also second bifurcation from the branches. So it has also been studied by Hamidi and Matteo, and they prove that for the second branch, so the ellipses, which is parameterized like this according to the Riemannian conformal mapping, Riemann conformal mapping. Okay, you have a parameter Q, and so you still can bifurcate from this Q. Okay. So basically, they found that for Q solution of this equation, you can bifurcate at this angular velocity. And the symmetry in this case is either 2 or 1. So we have one axis of symmetry or two axes of symmetries for the solutions, which are in the second branch. And if you take 3 branches, then it's 1 to 1, 1 to 1 extra. Okay, so there is okay, so this is for the ellipse, bifurcation from the ellipse, and you have this F. So remember this F. Okay. So basically, until now, I only discussed about simply connected patches, the disk or the ellipses. But we can wonder what happens close to an annulus. And so it has been done by Delahaus, Hamidi, Matteo, and Radial. And they found, using the same techniques, that this time you have 2 branches of bifurcation for given symmetries. And they are well separated and well ordered. And it happens for this constraint. And the constraint is related to the same F as the ellipse case. Okay. So you have a hole for the annulus, which is topologically completely different from the ellipse, but it's related to the same F. And we don't understand why. Actually, we have some some clue from Joukowsky transformation, which sends disk into ellipses. So basically, in the degenerate case, the circle inside of the annulus, you can transform it to a segment. So basically, we think that this is the reason why we can relate this back. Of course, analytically, it's horrible. So we don't know yet. Okay. And here in particular, so basically in the proof, you have a polynomial of the K2 to solve, to find the omega. So you have two roots related to the fact that the discriminant is strictly positive. Okay. But if it is 0, which corresponds to exactly the case equals to 0 here, it has also been done, but it involves more computation. Go further in the Taylor expansion of your function. So the solution of these equations are either the couple 2b or NB between 0 and 1, or NBN, or some BN, discrete BN, which tends to 1. So here B is the same between 0 and 1. So we take the annulus, reduce 1 outside and B inside. Okay, and so they could prove also bifurcation in this case for twofold matrix, so two axes of symmetries. And it does not exist for simple symmetries for n larger than 2. Okay, so this Bn will be important in the sequel for our main theory. Okay. Yes, I want to say that these angular velocities actually, so they are well ordered, as I said. So numerically, you can see this. So basically, this branch corresponds to omega n plus, and this branch to omega n minus. And you can see that for omega n minus, there is an analytic concentration to 0. So this is a problem because for KAM theory, you need some non-resonance conditions, and an analytic convergence to 0. This is not good for non-resonance conditions. Okay, basically, you want algebraic something to have algebraic loss of the reality. So algebraic decay in this case. So this is not good. Yeah. I mentioned that for other type of models, you could also find vortex patches, which are uniformly rotating in time. So for instance, if you restrict the equation not in R2, but in the unit disk, which in this case, the gain function is given by this. So you can also find simply and doubly connected vortex patch solution uniformly rotating in time. For SQG alpha, we have basically the green function is given by 1 over x to the alpha. Times time constant with the Euler function. It has been mainly studied basically because the range of alpha, the more alpha is, the bigger is alpha, the more singular is the equation. So to reach high values of alpha, it's more difficult. So you have to split into several figures, basically. Okay. So these two models are models that you can find in the study of the atmosphere.
Sorry, I don't understand what is the range of alpha.
Yeah. So alpha is between 0 and 1.
0 and 1.
Yeah. So basically the proof for 0 and 1 half. 0 and 1 half also for the simply connected, double connected. They extended for all the range of alpha except 1. And now we have other cases are. Yeah. Okay. So for this equation, it has been done by director, his former student, a physicist, and myself in the public case. And for Euler alpha equation, where the gain function is given by the difference between the one of Euler in R2 and this one, for lambda equals 1 over alpha, I proved it for the simply connected case, but not yet for the doubly connected. Okay. So let's move to the presentation of quasi-periodic solutions in general. So what is a quasi-periodic function? A quasi-periodic function is a function that you can write basically f of t equals f of omega t, or omega, a vector in order, whose component are non-rationally dependent. The generalization of periodic solutions, if you take d equals 1, it is exactly periodic solution with frequency omega 1. So such type of solutions, basically you can see it in the dynamical point of view as a function of t. T gives f of t theta, and in the phase space in theta, you can see it as a solution living in the torus of dimension d, and this condition tells you that the trajectory in the torus is that. Okay, so this type of solution appears first in a finite dimensional Hamiltonian system, which are integrable. So what is an integrable Hamiltonian system? It's a system, a Hamiltonian system, such that you can find a symplectic transformation, such that in the new coordinates called action angle, basically the dynamics no longer depends on theta, only on the action. So you can integrate easily this equation, and you find that the action are constant, and for a given action, the rotation for the angles in the torus are given by a linear flow omega t. Okay, so this is where it appears the f of omega t. So for integrable system, it's trivial, almost by definition. And then you can ask what happens for a perturbation of integrable Hamiltonian system. So it does not depend on theta, so it depends only on I, integrable Hamiltonian system. And the answer is positive under some suitable non-degeneracy condition and regularity condition. Actually, you can extract from P some information, let's say, to construct the whole, after a sequence of transformations, the whole dynamics, which is given by basically. It's not exactly this, but this is the idea. Okay, so at each time of the transformation, at each iteration of the procedure to construct from extracting from P some information, basically you have to face a problem which is called the small divisor problem. So let us illustrate this problem by solving this simple equation, which is basically the fundamental theorem of calculus, dtf equals g, but for dt in the quasi-periodic world, that is to say omega standard word. So I denote the variable which lives in TD. In the definition of a quasi-periodic solution here, so this is f of omega t, and f is periodic. We call the variable. Okay. So if you want to solve the equation, I'll use Fourier, and basically you have to divide by omega scalar m, but this can be small, okay, according to the Diophantine approximation of omega. Okay. So basically, the idea of Kolmogorov has been to introduce some so-called Diophantine conditions to control the size of the denominator by an algebraic loss of regularity if you estimate in AJS. Okay. If you take the HS now of this and you know that you can control the denominator like this, then you will use two derivatives of HS. Okay. So I said under non-degeneracy and conditions. So this is basically the non-degeneracy condition. And I said also regularity conditions. And basically this is related to this loss of regularity. Because if you are in analytic setting, an algebraic loss of regularity is not that bad. But if you are in finitely many differentiable situation, this is a real problem. Okay. And so to overcome the problem in the situation of finitely many differentiable case, you have to use what is called the Nash-Moser scheme, which which is a modified version of the Newton method. Where here, instead of having a df at un minus 1, which is not bounded, you replace it by projection on where you cut in Fourier at some good level. Okay. So you take the first Fourier mode until the mode nn, and you choose nn to grow fast enough to make the scheme converge. So you modify the Newton method like this, and for the analytical part, to make the convergence appear, you have to assume that so your function has nice so-called time estimates like this, and also you can find the right inverse, or almost right inverse if you add error terms here. So you find the right inverse, which also has some nice time estimates. And if you have this, then basically in your Newton method, it will be the same as before, the constant which grows, but quadratic, the convergence, plus some fast decay in Fourier times something, but you reach a higher level of regularity. So you cannot just stay in one HS space. You have to basically use all the HS coordinates between some in a range to make the scheme converge. And basically, you need 3 Sobolev level of regularity. So 1 for make UN converge, 1 to control in high norm, and 1 to make UN converge. And the argument is an induction. Okay. I want to say that this scheme is very robust and extremely flexible. So you can use it in many situations where you have basically this. This is not really restricted. Almost all that you can know satisfy this type of estimates. But if you lose some derivative, it's a good tool. And actually, it comes from Nash work in geometry, okay, for the isometric bed. So here we use it in analysis. You can see that the range is very large. Okay. So this was all I wanted to say about KAM theory in finite dimension, even if there are some other works. And for extending it to infinite dimension, that is for PDEs, it has been done by many people. First, starting with Schrödinger and wave equations, basically with the work of Kuchlin, Craig Wayne, and after some in the 80s and 90s, and recently, of course, Tassignano and collaborators extended it to a lot of class of equations like KD equation, lot of waves, where each time the difficulty increases according to the fact that your PD is quasi-linear and not. There are plenty of works. And for Euler equation, basically there is almost no results now, only these few ones, plus the one that I will present. The first result goes back to Nicolas Cousin and Awan Faou, where they proved for the 2D Euler equation in the periodic setting the emergence of explicit quasi-periodic solutions. So here there is no KAM theory which appears. Recently, so last year and this year, has been extended for the 3D case, still in the periodic box. And for the 3D with the forcing term, has been also studied by Christopher and in Okay. What about the vortex patch class? So all the results that we know are the one in this slide. So basically for SQG, Charcteristic equation and Euler equation, close to the disk. So it has been done last year, 2 years ago. And in this case, to have the Diophantine conditions, we have to select the parameter, a parameter to ensure these Diophantine conditions. Okay. So in these three equations, you have a parameter already inside the equation, so you can play with it. But for Euler equation, you don't have a parameter in the equation. So what do? Well, you use a geometrical argument to create one. So close to the ellipse, basically the parameter will be the eccentricity, and we'll play with the eccentricity of the ellipse to generate quasi-periodic solutions. If you restrict Euler equation in the disk, then all the radial solutions are not equivalent because the problem is not invariant by radial dilation. Okay. So all the disk solutions, trivial solutions, are not equivalent. So in this case, you can parameterize by a parameter B and bifurcate basically from this B. Okay. I say bifurcating, but it's not bifurcation, but this is what it says. And recently, so what I will present to you is close to an annulus, and this time the internal radius will play this role in the parameter. Okay, so now let's enter into details. So how to obtain quasi-periodic solutions close to the annulus using B as a parameter. So first, you take an ansatz for the boundaries, the parametrization of the boundaries. So you take a polar parametrization, okay, and the radius makes appear 1 or okay. And you take this square root because you want Hamiltonian system, infinite dimension. So the Hamiltonian system is given by this Hamiltonian, which is related to the kinetic energy and the angular momentum. And the symplectic structure is given by this d theta minus d theta. Where theta is the variable parameterizing the batch. Okay. I just mentioned now that we take a parameterization in a rotating frame. Okay. This omega is important because it will prevent the analytical convergence that I introduced you before for the eigenvalues. Okay. So we
take the parameter which parameterize which boundary. You have two.
both. It's a KK12. So one is the first boundary, 2 is the second boundary. And so this Hamiltonian system is satisfied by the R1 and R2, which are here, or the radial deformation of the batch. This is the unknown. A couple of unknowns. So you have two unknowns, and actually this Hamiltonian equation is of transport type, nonlinear, and it makes appear a coupling between the radial deformations. Okay. So since the Hamiltonian structure is given by this, the symplectic structure is given by the d theta minus d theta, then you see that the average of R1 and R2 are preserved in time. If you differentiate the d theta, here we have d theta something against d theta, so it's 0. So we take it equal to 0. Okay, we choose the average of our solution to be 0. So basically, it will be really an average at the annulus. Okay. So we restrict our phase space of functions and the variable theta to the L2 space where there is no average. Okay. Also, when you look for solutions to an equation, it is good to look at the symmetries which satisfy the equations. And so in this case, you have two types of symmetries which are given by this evolution. So if this is a solution, then under this evolution, this is also a solution. So we call it a reversible Hamiltonian. So basically, we look solution in the form of cosines because of this. And also the n-fold preserving property So if you have a solution which is n-fold, so R of theta is equal to R of theta plus 2 pi over m, then if you have a solution like this, if you have a solution like this, then under this transformation is also solution. Actually, here you can replace by any theta actually, and this is the invariant. So you have an invariant by translation in the space. So in our case, we love beautiful things, so we will look for n-fold solutions. The theta that we choose is this. It's not a technical restriction. We will discuss about it. So basically, our phase space for R1 and R2 will be restricted to the space with n-fold symmetry. So you restrict your Fourier modes to the lattice MZ. Okay. So I said that you want to find a solution to an equation. So basically, the first thing that you look at is the linearized operator. And if it has a good structure, then you can conclude by local inversion theorem or something like this, a piece of function theorem. And as I said, as I introduced before, of course, we will use the Nash-Moser because we have a loss of derivative, a loss of derivative. So let us discuss the structure of the linearized operator. So the linearized operator is given by this matrix. So you have the symplectic structure here against this matrix, where you linearize at a position R in a direction, let's say ρ1, ρ2. Okay. So the linearized operator is given by this. And in particular, if you look at the antidiagonal terms, which are given by this, so AKN is given by this. So if K is different from N, the radius here is close to 1, let's say, and the other one close to B at the converse. So they are well separated. So basically, the kernel here is smooth. And so this operator is smoothing at any order. So the antidiagonal parts are smooth. So this is a good point. And for the diagonal part, basically you have order 0 operator, but with the symplectic structure here, you will have order 1. So transfer operator. Okay. And what we want to say? Okay, maybe in the next slide.
V1 is a function.
Yes, V1 is this guy.
And L1 is a
L1 is an local operator. Order 0 and order minus. Why of order 0? Because basically, if you take K equals N, you have the same. You can basically factorize, take the annulus. Okay? You have exponential theta, exponential eta. So you have a sign. So you have the log of a sign. So basically, you have the Hilbert transform, which is order 0. So these terms are order 0, and the equilibrium is the Hilbert transform. Right.
very similar to the
what do you mean by the circle? Yeah, if you linearize or close to the ranking, you have and this is a good observation, but basically the diagonal parts correspond to the self-interaction. Okay, so and the anti-diagonal part correspond to the interaction between the two boundaries. So this is normal that you recover the linearization at simply connected because this is the self-interaction.
Okay, but the interaction is smooth.
The interaction between both boundaries, yes, it's smoothing. So it's a good situation. Okay. So if you look at the linearized operator, but at the equilibrium this time, so R equals 0, 0, which is the annulus, then the linearized operator becomes a matrix Fourier multiplier, and the matrix is given by this. So basically here you have your V1 and V2 at R equals to 0. So you see here that if you did not introduce omega, this would be 0, which corresponds to the analytic part. So this would be a determinal phase. So we need really this omega to prevent this. Okay, and the anti-diagonal part are given by b to the j, which is geometrically decaying to 0, which corresponds to the Radial, in particular, regularizing at the level. Okay, so you want to look at the eigenvalues of this, which are given basically by j time the eigenvalues found at the periodic level. Okay. Shifted by omega. So, in particular, here you see that for j equal 2, this is always 0, this quantity. So it corresponds to a double eigenvalue. So when you try to do some KAM theory, having a double eigenvalue or multiple eigenvalue is not a good situation in general. You have to do extremely refined analysis to study this. So we prefer to avoid this situation, which is already complicated. And this is why we restrict to higher symmetries, say m larger than 3. Plus, this quantity sometimes is not negative, so it's positive. And the eigenvalue here have some, let's say, real part, because here you have an I. It's not the imaginary part of the real part. So this corresponds to the so-called hyperbolic direction. Okay, and so it can make appear some degeneracy. Your solution can grow, can have some filamentation effect, maybe. So this corresponds to instability. Okay. Not always. So having a real part is not good for our frequencies. And so this is also a reason why we push the symmetries, because for j large enough, this is extremely small and this part is negative. And this prevents this term to be imaginary, and so this to have real part. So actually the restriction to the higher symmetry is not, it's a really an important point.
So sorry, the eigenvalue are not always
purely imaginary, not for small j, for small Fourier mod. They are not.
but for small d.
So a priori we fix a range of b, and we push the symmetries. We could do the converse, and actually it would say that b should be extremely small. So it's not that interesting because you want a huge class of annulus, which you replicate. Even if you want to push the symmetries, but you have solution close to this, instead of the converse. You have small symmetries, but for a small range of solutions. It's better. Okay. Actually, we could involve the hyperbolic directions also in the analysis, but it's more complicated. Okay. So the analysis at the equilibrium is difficult because we have different tricks. We don't know how to deal with it. So the point should be to diagonalize this. Okay, and so this is when computed the eigenvalue. And actually, you can diagonalize by conjugating by a symplectic transformation, which is given by this eigenstructure. In particular, the AJ here are basically in B to J, so they are geometrically decaying in J. So it corresponds to a smoothing operator. So basically, you can find a symplectic transformation, which is a perturbation of the identity with smoothing operators, such that you can diagonalize your equilibrium state to have a good structure for the linearized operator, and so a good structure for the corresponding Hamiltonian when you transform under the symplectic transformation. Basically, it will be a harmonic oscillator corresponding to this frequency. Okay, so this is good because now we have a new Hamiltonian, which at the equilibrium is completely understandable thanks to these Hamiltonian oscillators. Okay. So at the equilibrium, we can find this quasi-periodic solution for the equilibrium. And they are given by this type of solution. Basically, you solve the linear system, which is solved by the Fourier coefficients according to the matrix that you found. So you have 2 times 2 differential. You have a linear differential system that you can solve because you know the eigenvalues. And so you can find this type of solution which are reversible and full because you respect the frequencies to the lattice. Okay. And to have quasi-periodic solution, you have to have your omega to be with non-rationally dependent components. And so this is why we have to impose here the fact that the 2 sets of Fourier modes which are exciting our solutions are disjoint. So basically, this part is not true. This is not true what I said. Basically, this part will excite the external boundary, and this part the internal one. We have the oscillations. But of course, you have a symplectic transformation. It's not exactly true what I said. In fact, this is what we find. Okay, so the corresponding traversing vector is this guy, which are given by the eigenvalues that we discussed just before. And we want to impose some Fontaine condition. And we want to measure this set to see that we have indeed solutions, because if this set is empty or measure 0, it's not interesting. So how can we measure such a set? So for those who follow the course of Max, know that if 2 equals 1, basically we can do by hand. Okay. But for a generic, so a generic lemma is given by the Riemann lemma. So if you control the max of the derivative up to a certain order q of your function, which describes you some ball. So you look at the pre-image of a ball by f. So if you control from below the max of the derivatives, then you can control the measure of the set according to alpha and beta and the regularity of your function. Okay. So we want to apply this lemma with our omega f, and actually to prove the Riemann condition, so to prove this so-called transversality condition, you have to prove that your application B gives omega AB is not containing an hyper. This is a refined aspect of KAM theory, which is called non-degenerate KAM theory. So basically, if you have this, then you can conclude to the measure of the asset. Okay. And this is where appears the constraint that S1 and S2 are disjoint. Okay. So we had this type of solutions at the equilibrium. So basically, if we do some numerical simulation, because in this case this is explicit, this is the type of solution that we find. So you really see that you have solutions, quasi-periodic solution close to the annulus, and actually the frequencies here, and you see that the rotation is not the same for both, which corresponds to the fact that we have 2 different velocities. So basically V0, 1 and V0, 2 were not equal. One was equal to omega and the other one to omega plus. So this is why we have it. And the theorem which says that this solution that we can observe at the equilibrium level, we can also by a perturbation argument, extend them to the nonlinear equation. So this is the purpose of the theorem. So the theorem is the following. So you fix a priori some range of possible internal radius. You fix a symmetry large enough according to M, which was chosen such that we could avoid all the discussion of hyperbolic direction until like this. Okay. We fix two finite sets of all the models that we excite for constructing our quasi-periodic solutions, which are disjoint. Then, for omega large enough and for small enough a priori fixed amplitudes, you can find the set of possible B with asymptotically full measure in the range of B star below, B star above, such that for any B indistinct per set, you can construct a quasi-periodic solution with frequency vector, which is a perturbation of the equilibrium. And so the type of solutions, basically, they are exactly the one that we find at the equilibrium, but shifting a bit the frequencies, plus a perturbation with the same. So this is really a quasi-periodic solution. Okay, and this solution, of course, it's satisfied unfold symmetries because we choose the lattice M and Z, and also reversible because we have. So this is the theorem that we want to prove. So this ends the presentation of quasi-periodic solutions and the result that we have in the Vortex patch class for the annulus. And now we move to the proof of this result, really.
So sorry, Emeric, sorry to interrupt you.
Yeah.
But we were running out of time.
Ah, sorry.
How much time do you need?
Okay.
Next Friday it's free, and we are nobody.
Okay.
And AJS. So if you want to, maybe
I can summarize in a few minutes, I think.
Okay, 10 minutes are okay.
Yeah, 10 minutes will be okay. Okay. So basically, your equation at the nonlinear level will be a perturbation, a quasi-linear perturbation of the linear zone at the equilibrium. So we are in the situation where we have a perturbation of the integrable structure. So we use KAM theory. If you look at the solution, basically, we have a part which is localized in Fourier, so finite set, plus a perturbation. So we split the plate space into two parts. Basically, the one which corresponds to the first part, the one corresponding to the second part. We introduce the corresponding projectors. On this set, we introduce action angle variables. Okay. And so in the new variables, so action angle and normal variables, we can have an expression of our Hamiltonian, which is has a good normal form. And so basically we look with some quantum structure here. And basically, so you can reformulate the equation as looking at the zero of the functional, which corresponds to in the new variables the previous equation. Okay. So vertical theory tells you that to solve this equation, basically you only have to invert the linear operator, but restricted to the normal direction, not to the set where you are exciting the solution. In this set, you introduce the action angle variables, okay. And in this set, you can find the solutions by solving a triangular system under some nice diffeomorphism. And this is why you see that this you can invert, and here you have to restrict to the normal direction to solve the triangular system. Okay, in the variables action angle and so the linear operator is given by this. Okay. Basically, you have this structure for the linear operator. And you have a non-constant coefficient transport part plus constant coefficient nice part. plus assuming perturbation which is small. And the idea is to conjugate this operator to an operator which has a purely imaginary spectrum, which does not depend on the variable theta and phi. So first you do for the transport. So basically you conjugate by a symplectic diplomorphism like this. And actually the big part here, you can conjugate it to constant coefficients. And the structure is the same as before, but with constant velocities here, different. And a small part. This depends on R, where you linearize, but not this. And basically, after you conjugate again to kill this guy, and so you have a diagonal part. Okay. You have a diagonal operator. So you diagonalize, and to diagonalize, you have to use a suitable topology, okay, which makes the diagonal part and anti-diagonal part treated differently. Because basically the velocities are different. So for the anti-diagonal part, you will excite j plus j prime before you. So you have to consider another topology. Okay, so you can reduce to constant coefficient. You invert this one, and so you can come back because all your transformations were chosen continuous images. Great. So you can invert, and then you use the Nash-Moser scheme because you have nice time estimates. That's all the transformation of time. Okay, and at the end, so I finish with this. At the end, you end up with a solution in the variable b and omega, but the true problem is only involves b. So you have to rigidify the counter set, which generates your solutions. So basically, at each time when you invert, you have to introduce counter set. Okay. So you have to consider the intersection of all of the guide. And so you rigidify, as I said, and you look at the measure of this. And this is where the constraint omega large is. And you have this bound for the final counter set. So basically, if your perturbation is 7, so you choose perturbation. Smaller is epsilon, the bigger is the counter set. So basically, for almost all the values of B, if you choose the perturbation small enough, you can find the quasi-periodic structures. My seminar, are there any questions?
Since you showed the simulations, I have just a very super naive one. Have you ever tried to study what happens in on the
For the non-linear level?
Oh, so just for the linear level, if we assess the case, the more solution of how to decouple the like this one is a
At the beginning, I made a mistake and it was not a disjoint. And basically, there is no difference.
Okay, so do you think it's technical?
Huh?
Do you think the assumption that you make that S1 and S2 are
No, in the analysis, we really knew this, but analytically, maybe there are some compensation. Maybe numerically, there are some compensation.
Okay.
So, but I think that if you have some intersection, it will have a resonance.
I would suspect so. If you do not.
Yeah. But numerically, we don't see it.
So it's about the case when you are doing the part of discussion.
Yeah. So this part actually you can do by involving the hyperbolic direction in the normal component. You do not excite these hyperbolic directions. You put it in the normal part. And basically in all the analysis, you have to distinguish if you have hyperbolic or hyperbolic elliptic or elliptic situation. So basically in what I discussed, we only have elliptic situation. But you can do it. And actually in the work of Zinevasania, Berti, and Pasmudi, for the ellipse, they construct quasi-periodic solution close to 0%. They do this similarly. Yeah. And since I said that through the Joukowski transformation, we can relate maybe the annulus to the ellipse.
You believe there is not.
I believe that it should be the same. But you can only do in this way, from the annulus to the ellipse, because it's degenerate, cannot come back. So maybe if we do this, our result can, through this transformation, imply their result, but their result cannot imply their result.
Other question? Maybe I have a question. The condition on the unfold, and so the symmetry that you supposed. You said that it's not restricted to suppose that you have symmetry putting plus to 5 over, but it won't it for everything, right?
The Hamiltonian is invariant under any translation of the folk.
Okay, but you said that it's not restricted to suppose that only you have only this ratio.
No, actually, these so we had to push the symmetries to avoid the, as I said, the hyperbolic spectrum and the degeneracy also of the second mode, because there is also this point which is really difficult, and this does not into account. It does not enter in our previous discussion. This second mode, really, this is what was. So in the ellipse case, they had to face this because you have two axes of symmetry. So they had to face this. And to prevent this, you have to introduce another symplectic transformation related to the angular momentum to prevent this. So no, it's not restricted in this sense. You can do something that's more involved.
Okay.
Just a quello del fatto che global regularity theorem of that's one of course axes of the apply also in this case. It's not simply in that case. I mean the dynamics is the regularity of the vortex patches is
it's a local theorem.
local.
So what can happen is that your boundaries may be touched at some point, but it does not happen because you know that the solution is global. And for topological argument, you cannot escape your topological structure. So the result of Schumann, since it is a local theorem, let's say, it can apply also in this case. And maybe at infinite time you can have this. Sorry.
So at the solution, also if you outside the KAM tori that you find.
Outside this is another story. Outside, maybe you can have filamentation effect.
Okay.
So
was the question.
Yeah.
In general, you can have singularity.
No, you have filamentation. That's singularity. Filamentation effect. That let's say you start with a simply connected. Let's take a simply connected theorem.
Okay.
Then still keeping the area, you can maybe have this would correspond maybe to a growth of the sub-algorithm that for the non-chosen parameter, then maybe you should use some argument by order diffusion theory. So
also you remain in the smooth.
Yeah, you remain in HS in what we did for S large.
With a group. Okay.
I can have a group, but you are still in HS at any time.
Okay, so no more question. Thank you again.